Conduction and induction. Solids are a form of matter whose atoms form a fixed structure. Nuclei, with their protons and neutrons, are locked into position. Solids are classified as either conductors, insulators, or semiconductors. In conductors, some electrons are free to move through the solid and are not bound to any specific atom. Electrons are bound to their atoms in insulators and may move short distances, but much less than the electrons in a conductor. Semiconductors, depending on their situation, act as either conductors or insulators. In conductors, some electrons are mobile and can move freely inside and on the surface of the solid. Since electrons are repulsed by each other, because they're like charges, they will move as far away from each other as possible. Therefore, excess charge on a conductor will spread out evenly across the surface of the conductor. If a charged object is brought near one side of a conductor, charges can shift to one side. This is called polarization. Insulators are materials that have strongly bound electrons that can move only short distances within the solid. Different insulators have varying levels of insulation capabilities. If a charged object is brought near one side of an insulator, charges can shift to one side of their atom. Polarization in an insulator is weaker than in a conductor. Before a discussion of conduction and induction can take place, the concept of the ground needs to be understood. Electrons can flow between objects, both conductors and insulators. Electrons can also flow from Earth, which is an excellent conductor, to the objects and from the objects to Earth. Because of its massive size, the Earth serves as the ultimate source and destination for electrons. The concept of grounding will be discussed further in the electric potential unit of this course. When a wire is attached between the Earth and a negatively charged conductor, excess electrons flow to the Earth, leaving the conductor neutral. This is called grounding. A positively charged object will cause electrons to flow to it from the ground. When you touch an object with a net negative charge, you may get a shock. This is because the conductor wants to get rid of its excess electrons. To do this, electrons flow through you to the ground. If the conductor had an excess positive charge, the electrons would flow from the Earth to you. In either case, there's a spark. Note, grounding used to be called earthing because the flow of electrons to and from the Earth. Electrical circuits and devices are usually grounded to protect them from accumulating a net charge that could shock you. To ground an electrical device, a conductor must run from the device into the ground. Plugs for many electrical devices have a third grounding pin that connects to a wire in the outlet box, which goes to the ground. Click here for a video demonstration of a Van de Graaff generator. Charging by conduction involves conductors that are insulated from the ground, touching and transferring the charge between them. The insulator is necessary to prevent electrons from leaving or entering the spheres from the Earth. So here we have two spheres, two conducting spheres. This one has a charge of -4Q. This one has a charge of 0, so it is neutral. These are identical spheres and they're very far apart. Note, Q is the symbol for charge in coulombs. If the spheres are brought together to touch, their electrons push as far apart as they can, and the total charge is distributed equally between the two spheres. Note that the total charge stays the same. And remember, similar charges repel. After they touch, the spheres are then moved far apart again. The total charge is still -4. But now this sphere has a charge of -2, and this sphere also has a charge of -2. That is because air serves as an excellent insulator, and the charges can't get back to where they started from. And this results in an equal distribution of charge. To figure out what the charge on each conducting sphere will be after making contact, you just average the charges together. So for example, if we have a charged sphere with +7 charge, and over here we have a sphere with -3 charge, After they touch, as long as they're identical spheres with identical sizes, then you just average them together. Plus 7, then you're going to add -3, so it becomes 7 minus 3, divide by the number of spheres, 2, and we see that both spheres will have a positive 2 charge after they make contact. Here's a sample problem. If a conductor carrying a net charge of positive 8Q is brought into contact with an identical conductor with no net charge, what will be the charge on each conductor after they are separated? They're going to split the charge, so we just average them together. One sphere has a charge of 8, the other one 0. 8 plus 0 divided by the number of spheres is 4 per sphere. Here's another problem. Metal sphere A has a charge of -2Q, and an identical metal sphere B has a charge of -4Q. If they're brought into contact with each other and then separated, what is the final charge on sphere B? All right, so we just have to average them together. -2 plus -4 divided by 2, the number of spheres, and you'll see that each sphere then has a charge of -3. They share the extra electrons. Here's another problem. Conducting sphere A is brought into contact with conducting sphere B and then removed. Sphere B is then brought into contact with conducting sphere C, then removed. What is the net charge on each sphere after the interaction? All right, so here's our before scenario. So first, A and B touch. So we average +2 and -4, and we see that both A and B would then have a charge of -1. However, then B and C touch. So after A and B touch, then B would become -1. So then -1 and 1, they touch and they even out. They become neutralized. Therefore, A will have that charge of -1, and B and C will both have no charge. Charging by induction involves charging objects without having them make contact. This is a neutral conducting sphere connected to the ground via a wire. A negatively charged rod is brought near but does not touch the sphere. Electrons within the sphere are repelled by the rod, and they pass through the wire down into the ground, leaving behind a net positive charge on the sphere. So here you can see the electrons are being pushed down into the ground along this wire. While the negatively charged rod remains near the sphere, the ground wire is removed. Note that there can be no more movement of electrons to and from the sphere, since the sphere is isolated from the ground. Electrons cannot jump the gap between the rod and the sphere, or between the ground and the sphere. The wire here is removed, disconnecting the sphere from the ground, eliminating the path through which electrons can travel. The rod is then removed. It's important to note that the charge on the rod remains constant. It's still negative. The charge on the sphere is now positive, as it lost electrons to Earth. Through physical contact, a charged object will transfer a portion of its charge to a neutral object. Because of the conservation of charge, the amount of charge on the initially charged object will decrease. For example, a positively charged object has more protons than electrons. Therefore, when it touches a neutral object, some electrons from the neutral object will transfer to the positively charged object. This leaves the neutral object with a positive charge, since it is now also missing electrons. The amount of positive charge on the initial object will decrease by the same amount of charge that the neutral object gains. Similarly, a negatively charged object will transfer negative charge to a neutral object. A charged rod will be brought close to a neutral grounded object, but it will not touch it. A positively charged rod will attract electrons from the ground to the neutral object. A negatively charged rod will repel electrons to the ground. The ground wire is then removed. The neutral object will be left with a charge opposite to the charged rod. The rod will not lose any charge. The extra charge on the originally neutral object comes from the ground. As long as the ground is disconnected before the initial object is removed, the neutral object will gain charge. If the ground were left in place, once the charged rod is removed, the neutral object will pass its gained charge back to the ground. Here's an experimental design problem. Two identical neutral metal spheres are placed on insulated stands. Describe an experiment that will allow you to charge the spheres with equal and opposite amounts of charge. You can connect the spheres with a wire, like this, and bring a charged plastic rod close to one of the spheres. Let's say it's a positively charged rod, so electrons from the right sphere are going to be attracted to it, and they're going to end up on the left sphere. They're going to go across the wire this way and end up over here. So if this rod was charged with a positive charge, the sphere that was close to the rod will end up negatively charged. The other sphere will gain an equal amount of positive charge because it's just due to the missing electrons. So while the rod is still close, you should disconnect the wire, and that will leave the two spheres equal and oppositely charged.